kind of moving beyond genetics and into autoimmunity in UK Biobank. Professor Stephen Sawcer from the University of Cambridge is going to talk about, I think, opportunities, if you like, within UK Biobank. Stephen.
Thank you very much for inviting me. It's an enormous pleasure and privilege to be included in the first meeting. I do feel a little bit like a parasite. I mean, this morning was very humbling to see the enormous amount of work that has been done by an enormous amount of people and the generosity of the participants. So this is about using that resource. I think your immune system is essential. Without an immune system, you will not last very long. It's there to protect you from bacteria and cancer and the rest. But occasionally it goes wrong. Occasionally it will damage the body. There will be too much inflammation and tissues and organs will be damaged. And these diseases we refer to as autoimmune diseases. So we all have that sort of intuitive idea about what an autoimmune disease is, but it's quite hard to write a succinct definition of autoimmunity that's agreed by all experts. Some people like to sort of restrict autoimmunity to just those reactions where there's been a loss of tolerance. Your immune system has to recognize what's a bacteria and what's healthy, normal tissue. What should I attack and what should I leave alone? And that sort of adaptive immune system, if there's faults in those lymphocytes that control that, then some people restrict the idea of autoimmunity just to those types of diseases. And others point out that your immune system can be non-specifically activated. The innate immune system can turn on inflammation that can damage tissues out of proportion to the insult in those diseases. And so we have the concept of auto-inflammatory conditions. In some people's minds, these things are sort of mutually exclusive. A disease is either autoimmune, i.e. due to a problem with the lymphocytes, a failure of tolerance, an overreaction to danger signals, or is some problem in the innate immune system where there's a non-specific activation of the powerful mechanisms within the immune system. But about a decade ago, these authors pointed out that it's probably more helpful to think of diseases as having these type of autoimmune diseases, having some component of both. In other words, these are dimensions of immune-mediated inflammatory diseases. There's the autoimmune, the adaptive part, and the auto-inflammatory, the innate part. And they speculated, based on the available evidence a decade ago, where diseases would lie. So these are sort of rare monogenic causes of purely auto-inflammatory disease, familial Mediterranean fevers, and these sort of lymphoproliferative disorders where there's an outbreak of autoimmune tissue-specific damage. These are monogenic forms at the two extremes, and then they could place most of the diseases that we would think about as being autoimmune diseases somewhere on this spectrum, with some being more auto-inflammatory and some being more autoimmune. So altogether, there are about 100 or so, there's more than 100 different diseases that are considered to be part of these immune-mediated inflammatory disorders. So individually, most of them are not terribly common. So even in a big resource like Biobank with 500,000 people, there aren't enormous numbers of some of these conditions. But some of the more common ones, Biobank includes large numbers of people with these conditions. And collectively, autoimmunity affects between 5 and 10% of people. So in other words, 1 in 20, 1 in 10 people in Biobank, 1 in 20 people in the country have some form of autoimmune disease. These are some of the more common autoimmune diseases. This is their prevalence per 100,000. This measure here is how much is my risk increased if I have a brother or sister with that particular condition. And that's a characteristic feature of these diseases, that they cluster in families. So if someone in your family has an autoimmune disease, you're more likely to get that autoimmune disease. And these measures tell you by how many times am I more likely to get this condition if someone else in my family has that condition. In terms of genome-wide association studies, there are few areas of medicine that have been as successful as autoimmunity. Because of these marked familial clustering, which implies underlying genetic causes, genome-wide association studies have been fabulously successful at identifying causal variants, the SNPs that Claire was talking to us about, those changes in the sequence that increase the risk of developing these diseases. There's a sort of strange inverse relationship between the prevalence and the number of loci that have been found. So if you take that information, which is nicely summarized in a publicly available database called Immunobase, and you take the existing data that we know from the published genome-wide association studies and ask how similar are different genetic conditions, in the same way that Claire was showing you how you can compare how similar people's ethnic backgrounds are using genetics, and you can compare how similar these different diseases are to each other. And in that same sort of plot against what we call these principal components, the main continuous measures of adaptive immune response or innate immune response, they reproduce that pattern that was predicted 10 years ago. That's predicted on the basis of clinical observations. These diseases cluster together. We know that people with ankylosing spondylitis, many of them have inflammatory bowel disease clinically or subclinically, etc. So this clustering of these diseases, the similarities in the genetic backgrounds, suggests that even though individually they're not very frequent, there may be much gained by looking at a large resource like Biobank and comparing and contrasting these different diseases. So this is just to give you an idea of the sort of number of cases that have been studied in the published GWAS studies and the number of cases that are available in the first 150,000 and in the full Biobank data set. So for some of these, we have significantly more cases than have ever been looked at before. So there will clearly be new discovery in those conditions, and in some, there are not so many more than have been studied. So it'll only be incremental in terms of the number of new loci that we might find. But the main principle behind this is to try and compare and contrast these diseases, to learn from the overlap between them, the similarities and the differences. This is just to give you some idea of the first 150,000. These are these Manhattan plots, which we keep showing you all the time, just to remind you again. This is the genome. These are the different chromosomes. So each dot is one of the 800,000 SNPs that was tested. And the higher it up it is, the more significantly associated it is. In other words, the higher that frequency is amongst the cases than it is amongst the controls. And anything above this red line we're really interested in, and things above the blue line we're probably still interested in. So you can see that we've made a substantial number of new discoveries about what might be considered the archetypal autoimmune disease. This is zooming in. So this is the same sort of plot that I've just shown you, except I'm zooming in just to those peaks to show you in more detail the total number of SNPs that have been looked at, and also the fact that we'll be able to tell which of these SNPs is driving this association, because these variants that are near to each other, they're correlated with each other. So when you see associating with one, you tend to see association with the other, and you need large sample sizes to be able to say that that's the SNP that's driving it and not some SNP that's nearby. That's another advantage of this very large resource, is we'll be able to fine-tune exactly what SNP it is that's driving that association. So I'm not going to take you through every single one of these, but some of them, of course, have rather small sample sizes. And we know in this type of study, for these type of effects, really, unless the sample size is 1,000 or 2,000 cases, we're not going to get very much reliable signal. But of course, we can combine this data with other data that we already have published to boost the signal. So whether you include aspirin in an immune-mediated disease, one could make an argument, but it's certainly a very large number of cases. Certainly that would be one of the single largest studies ever done in asthma, and a large number of novel signals. But the extra information that's in Biobank, all that additional phenotype information, allows you to do tests very easily. So this is a simple stratification on the basis of age, because we know that mechanistically asthma at a younger age is different from asthma at a later age. So if you just compare those cases, you see this very well-known signal on chromosome 17 that picks out those who have younger onset asthma. Of course, there are lots of exciting biomarkers coming, things like the ANA and the rheumatoid factor, that we might be able to do genome-wide association studies, those autoantibodies that we know are manifestations of autoimmune disease. Another thing is just to simply take all of the traits together. So although individually, specific ones may not have very large numbers, if we put them together, then the sort of total number of people with some autoimmune disease or other within Biobank is really very large. So this plot here is distorted. This is the highest SNP, the highest value in any disease across all the different traits. And then this is just literally lumping all of the traits together and saying, I want to test autoimmunity. Are there any consistent signals where I'm seeing association that increases the risk of your immune system reacting abnormally rather than producing a particular disease? One of the strongest things that you will have noticed is this constant, almost constant, very large signal on chromosome 6. So this is the major histocompatibility complex. This is where the HLA genes, the genes that determine your tissue type. When you have a transplant, you have to have your tissue matched. Otherwise, your immune system will react. And the molecule, the genes that control those marker proteins are called the HLA genes, and they lie in the major histocompatibility context. And lots of autoimmune diseases are strongly associated with particular autoimmunity. We've been able to use the SNP data in the way that Jonathan explained to you to infer which tissue types people are carrying and have established the expected distribution of associations. And obviously, with the larger number, we'll be able to fine-tune those and discover additional signals in those regions. So just wanted to finish with this. This has come up quite a few times about the question of authenticating or validating or how reliable is a self-reported diagnosis. All the analysis I've shown you is based on people saying, I've got that disease or I haven't got that disease. Kathy was describing how there are enormous efforts to try and authenticate this, to develop algorithms that allow us to know whether that's correct or not. But the genetics can help with that. So this is the MS genetic load. So if we take the known MS SNPs and we measure how many do you carry, how many of the risk alleles do you carry, the dotted line is what a control person would carry, someone who doesn't have MS. And this distribution is what we saw in our known cases that we used in the GWAS. The red line is the predicted value. This is what we saw in people where the hospital records in Biobank said they had MS. This is the ones where people self-reported as having MS, and this is the combined. Now, this is slightly lower than the red line. In fact, all of them are slightly lower than the red line, but that's about discovery. There's a regression to the mean. The identified effects in the discovery studies are always slightly larger than the real effects. So there's a very substantial genetic evidence of reliability in the diagnosis, and that's a well-established feature of autoimmune disease as well. Not very many of these diseases have specific diagnostic tests. Most of them are diagnosed clinically, and pathological studies show that that diagnosis is very robust. Finally, this is just to say that GWAS are incredibly forgiving of this type of issue. So this shows you the accuracy of the diagnosis and the impact on the power. So you really have to be quite bad. You really have to do very badly at making the diagnosis before you lose very much power in your genome-wide association study, as long as you have a substantial number of people. So this is the different sample sizes, 10,000 cases and controls, 2,000 cases and controls. So if you're in the middle of the range, then there's more impact. So if it's the case that a proportion of the people who have self-reported as having MS or have self-reported as having thyroid disease don't actually have it, that will impact my power a little bit, but perhaps not as much as you might at first think. Thanks.